Let's take a look now at the idea of trigonometric substitution. Now that we know how to integrate the powers of trigonometric functions, we can use trigonometric substitutions to integrate radicals that have this form. Because right now, if you just have an integral that looks something like this, you really wouldn't know how to deal with it. The basic idea is to use trig substitutions to eliminate the radical in the integrand and then use the Pythagorean identities. Now there's a couple of identities that you really need to remember. First of all, start off with our, as we call, sine squared of, let's use x, plus cosine squared x is equal to 1. That's your basic Pythagorean identity. And then from here, we can write cosine squared as being 1 minus sine squared. This is an important identity we'll be using. Secant squared equals tangent squared plus 1. And then obviously this also would then imply, give us this last identity that we'll use, that tangent squared must be equal to secant squared minus 1. So keep these in mind because they're going to be extremely important here shortly. So let's take a look here. For a greater than 0, if I have something of this form, a squared, a constant, minus u squared, I will use the trig substitution. Let's let u equal a sine theta. That would then imply that a squared minus a sine theta squared, square root of all of this, is actually equal to this. Because all I did is I said u was a sine theta, so here's my u squared. So I still have a squared minus u squared. But that will give me, I'll write this out one more time, a squared minus a squared sine squared theta. Of course, that's still under the radical. But this a will factor out. The a squared will come out as an a, so I have a times the square root of 1 minus sine squared theta. But we all know that 1 minus sine squared is cosine squared, so this is actually equal to a times the square root of cosine squared theta. And of course, the square root of cosine squared is just cosine, so this equals a cosine theta. So I went from something that looked like this, where u is probably be a function of x, or it could just be in x squared, and I let u equal a sine theta, use this trig substitution, and it got rid of the radical and gave me something that I should not have a difficult time integrating with. Now what's important here is I would now be integrating a cosine theta, but I need to ultimately get this back to u. So we can't forget to change back to u. So let's take a look at this. This has that same form, where a here, in this particular case, a would be equal to 5, because 5 squared is 25. So this has the form a squared minus u is x, x squared. See, I'm seeing this form right there in the denominator. So I'm going to go ahead and let x equal 5 sine theta. That implies that sine theta equals x over 5. This will be important in a little while. Now dx will be 5 cosine theta. This is important because I will need to substitute that in for my dx. So what I have when I substitute all this stuff back in is I have the integral of x squared, but x is 5 sine theta. So this is 5 sine theta squared. There's my x squared, divided by the square root of 25 minus 5 sine theta squared. That took care of the 25 minus x squared. But I also have dx, and dx is 5 cosine theta. Oops, I forgot it here. This is 5 cosine theta d theta. So hopefully this is now something that I can integrate in a much easier fashion. Well, I have some more simplification to do. So I'm going to write this out again. This is actually 25 sine squared theta. And then I have a 5 cosine theta. It's right here. This, I have a 25 minus 25 sine theta squared. So at 25 I can factor out as a 5. This will give me a 5 times the square root of 1 minus sine squared. But 1 minus sine squared is cosine squared. So that takes care of that. D theta. I can cancel out this 5. The square root of cosine squared is cosine. So that I cancel out with this cosine. So really, what I'm integrating here is 25 sine squared theta d theta. So that, just treat like a new problem, because it is. This equals, I'm going to pull that constant out, 25 times the integral. Sine squared, I will write as 1 minus cosine squared, whoops, not cosine squared, I'm sorry. That's cosine 2 theta over 2. This is an identity we've worked with several times before. So if I pull this out, I'm going to write this as 25 over 2 times the integral of 1 minus cosine 2 theta d theta, which is 25 over 2 times, when I integrate this, I will get theta minus, well, I know the antiderivative of cosine is sine, so this has to be a sine of 2 theta. But when I take this derivative, I have an extra 2 here. So what I'm going to do is divide this by 2. And of course, we should put this constant of integration as plus c in there, because it is an indefinite integral. Now, I'm going to use one more identity because I know it's about to make my life a little bit easier. Sine of 2 theta can be written as 2 sine theta cosine theta, which means these 2's will cancel out, plus c. Okay, now remember way up here, we said that because of this substitution, I know that sine equals x over 5. That's actually pretty important. I'll write that down again. We know that sine of theta equals x over 5. That means I can go ahead and make my right triangle, which we've done before. Whoops, that's a right triangle. So this is theta. So if sine is x over 5, it must look like this, which means this is the square root of 25 minus x squared. Now from here, I can read off sine and cosine. Okay, I know sine is x over 5, so I'm going to rewrite my answer as 25 over 2 times, I'm going to come back and deal with this theta in just a second, minus sine of theta is x over 5. Cosine of theta is 25 minus x squared, square root of that, over 5. Of course, I have this plus c. So the only thing I'm missing here is this theta. What is this theta? Well, if sine of theta is x over 5, then arcsine of x over 5 is got to be theta. So there's my solution. I could simplify a little bit more. I suppose a few other things I could do with these 5s and 25 or whatever. But right now, I mean, that looks pretty good to me. And actually, I should clean this up because I have a paren here. I should have a paren right there. Yeah, that looks a little bit better.